So let's talk about those subatomic particles. Subatomic meaning smaller than the atom. All atoms have the same subatomic particles making them up. Oops. We've got protons and neutrons and electrons. As I mentioned earlier, the protons and the neutrons are nearly identical in mass. So the difference here is in the fourth significant figure. So for our purposes, we can say they have the same mass. The mass of an electron is significantly smaller. So an analogy to help you understand that is if the electron was a grain of rice, then the proton would be like a baseball. So protons are close to 2,000 times larger than electrons. And of course, so are neutrons. So kilograms and grams, like here they give the mass in kilograms, 9.1 times 10 to the minus 31 kilograms. I mean, you could use smaller metric prefixes that are smaller, but still kilogram is just not a real, the gram even is not useful for these things. So there's another unit that's more useful for measuring these extremely small things, and it's called the atomic mass unit. Atomic mass unit, abbreviated AMU. It has kind of a funny definition. One atomic mass unit is defined as 1/12 the mass of a carbon atom containing 6 protons and 6 neutrons. So the way that is defined means that a proton or a neutron has a mass that is very close to one atomic mass unit, because that carbon atom has 12 of these particles that have mass, plus some electrons that are so small that we don't really need to consider them. Charge of the proton and the electron are equal in magnitude but opposite in sign. And then the neutron has no charge. So what do you need to know about all of this? Well, you need to know the names of these particles. You need to know relative mass. So this is 1, this is 1, and this is 0. You need to know relative charge. The protons are positive, both start with P. Neutrons are neutral, no charge, both start with nu. Electron is negative. The homework might have you do questions involving where you need the mass of one of these particles, and you just come here and you look it up in the table. You don't memorize that. So matter is usually charge neutral because we have protons and electrons in equal numbers. But charge imbalances are possible, and when those occur, they tend to equilibrate or equalize quite quickly and sometimes rather violently. So an example of this is lightning. So lightning happens during storms when negative charge builds up on clouds and positive charge builds up on the ground. Nature doesn't like this separation of charge. And so when it gets to a point, then it will equalize and we'll have this electrical discharge that causes the clouds in the ground to equalize in their charge. Static electric shocks are just extremely small forms of lightning. Right? You shuffle your feet on carpeting and then you touch a metal door jamb and you get a little shock. Right? That's because of an imbalance in charge that built up. So the number of protons is important. The number of protons in the nucleus defines the element. So this is called the atomic number, and it's given the symbol Z from the German word Zahl, which means number, even though atomic number starts with A, but this was done in German. So here we have a helium atom, and in the nucleus we have 2 protons. Every helium atom has 2 protons. That's what makes it helium. Carbon atoms have 6 protons, always. So that's like identifies the atom as being of a particular element, the atomic number. These numbers are shown on the periodic table, and in fact the elements are arranged by their atomic number. So here we see in each little box, we see the chemical symbol for that element, and above it we see the atomic number. So that means that, well, let's pick up platinum. Here, this is platinum. So a platinum atom is going to have 78 protons in its nucleus. So the atomic number is unique to that element. Then we also have a chemical symbol, which is an abbreviation of that element's name. Chemical symbols are either 1 or 2 letters. They are shown on the periodic table on the wall and on the one you'll be given for exams. This one has the element symbols and the names, but the names take up too much space. There's a lot of other useful information, and so we don't typically see the names on the periodic table. So I've given you a list of element names and symbols that you're supposed to memorize. And there's actually an online quiz that's open that you're supposed to take. That's an assignment, right? On that. The element symbols, often they are the first letter of the element's name. Like, helium is He. Well, helium starts with He. That makes sense. Hydrogen is just H. So helium couldn't be just H because there was already one like that. So it has to be He. Chemical symbol for carbon is C. Then we get things like calcium, right? Calcium also starts with Ca, like carbon. So that one got to be Ca. And then we've got cadmium, also starts with Ca, but Ca was already taken. So now they went to the third letter of the name, Cd. And then we've got ones like sodium and potassium, thank you, and gold and lead. There's a bunch of them. Mercury, tungsten. You're like, where do they get this? There isn't an N or an A in the word sodium. That's because it was named from the Latin natrium. So it's the first 2 letters of the Latin name. So those ones that don't seem to make sense, there's a reason behind them. They weren't put there just to mess with you. But you can believe that if you want to. So all atoms of a given element have the same number of protons. Protons, they don't necessarily have the same number of neutrons. And this is where the atomic theory had to be adjusted a little bit. So if you have atoms that have the same number of protons, they are members of the same element, but being slightly different with neutrons, then they're called isotopes. So iso means the same. So these guys are the same, but they're different. So an example, looking at neon. Neon's element number 10 on the periodic table. All neon atoms have 10 protons. But some of them have 10 neutrons, some have 11 neutrons, and some have 12 neutrons. And knowing how many neutrons there are or which isotopes exist is not something that's easily predictable. We're not going to even try in this class. And then, so neon has 3 different isotopes. Well, does that mean a third have 10 neutrons and a third have 11 neutrons? No, it doesn't. There's relative amounts of each isotope, and those relative amounts are consistent, remarkably consistent, regardless of where the sample came from. But they just have to be experimentally determined. And so those relative amounts are generally expressed as a percentage. It's called the natural abundance. So, what percent of sodium atoms have 10 neutrons? What percent have 12 neutrons, etc.? So we can symbolize the different isotopes of an element using a symbol that follows this pattern. So here, this capital X, that's the chemical symbol, like Ne for neon. And then we have a superscript and a subscript to the left of the chemical symbol. On top is what's called the mass number. And so this is the sum of the massive particles, the protons and the neutrons. So that's the mass number, and that confusingly has the symbol A. So that's protons plus neutrons. And then down here we have the atomic number, which is not A, it's Z, and that is the number of protons. So 3 isotopes of neon can be written like this. What's kind of nice about this is if we stack these numbers, if we stack these up for subtracting, the big number's on top and the little number is below. And so 20 minus 10 is 10. So this is neutrons plus protons. This is protons, and this is neutrons. So if we want to know the number of neutrons, we just subtract these stacked numbers here. We can also indicate which isotope it is using the mass number after the element symbol or the element name. So here we have those 3 isotopes again. They all have the same number of protons, but the number of neutrons is slightly different, so their mass numbers are going to be different as well. And the natural abundance, I can't tell you why it is, it just is. So 90.48% is neon 20. So we should be able to do things like this. What are the atomic number, mass number, and symbol for the carbon isotope with 7 neutrons? And there's a periodic table here because we might need that. So carbon has the symbol C, and so this is the one referring to carbon. So the atomic number. What's the atomic number?
6.
It's going to be 6. So the atomic number Z equals 6. That tells us it has 6 protons. The mass number is equal to the number of protons plus the number of neutrons. Well, the problem tells us this one has 7 neutrons, right? So this must equal the mass number 6, the atomic number 6, plus the number of neutrons, or 13. Okay? And then the symbol, so the element symbol with the mass number on top to the left and the atomic number below. How many protons and neutrons are present in an atom of this? I'll call that potassium 39.
19 and 20.
19 and 20. Good. So how'd you get that?
The atomic number 19 is equal to the number of protons, and then mass number minus the atomic number is neutrons, which is 20.
Perfect. So this number down here is the atomic number. So that is 19, and that is equal to the number of protons. We can also kind of cheat and look at the periodic table to remind ourselves, oh, that's element number 19, if we forgot what those things mean. But then if we take the mass number minus the atomic number, that means there must be 20 neutrons. How many electrons?
19.
19. Same as the protons, because it has to be neutral. Okay? Okay, so number of electrons is equal to the number of protons. Now, in chemical changes, we can have electrons that gain, atoms. We can have atoms that lose or gain electrons. And when that happens, they're called ions. So an ion is an atom that either has extra electrons or lost some electrons, and so it has an electrical charge. So if sodium loses an electron, it had It had 11 protons and 11 neutrons, 11 protons and 11 electrons to start with. It loses an electron, now it has a +1 charge. And so it has a symbol, element symbol here with a positive superscript, and that's going to be a cation. So cations are positive. And a cat, positive. Anions are negative. So fluorine can gain an electron. Now it has one more electron than it does protons, and so it has a negative charge. So that's an anion, negatively charged ion. The ion charge is written as a superscript, and the magnitude is written first, followed by the sign. So why do we do it like that? Well, let's just look at sulfur. So sulfur often forms an anion with a -2 charge. And so we'll call that S2 minus instead of S minus 2. Because this looks like the variable raised to the -2 power, right? This looks like math stuff, and that's not what we're doing here. So I think the reason that the sign always comes afterwards is just to make sure it's not mistaken for an exponent. Now these do not have the number 1. It's not Na1 plus, it's just Na plus, right? And if we have calcium has a 2 plus charge.
That's just because the 1 is inferred, right?
The 1 is inferred, yeah. So I think of chemists as being kind of lazy in a way, or being efficient, right? If we don't need to write the number 1, we're going to just leave it off, right? So there's no number written here but a positive charge. So the only reasonable thing to assume is that it's 1 positive. If it was something else, the number would be there, right? Here, Ca2 plus, we need the positive charge, again, so we don't look like calcium squared, right? We don't want it like that. So the magnitude comes first, followed by the sign, and if it's a number 1, we usually don't write the number 1. You'll see a whole bunch of examples where we don't do that. In fact, this looks weird to me because normally we wouldn't write the 1 there either. Any questions?